Okay, good. So today we're going to start talking about simultaneous localization and mapping. That's the course that we're here for. Um, but we're going to start slowly with reviewing two of the most important concepts and topics in probability and statistics. And the reason for that is because SLAM is all about probability and statistics. It's a very interesting algorithm because at the core of it, it solves a problem that was previously impossible to solve. It makes that tractable by clever use of statistics. So I like it. I think it's a very elegant, very particle filters in particular, a very elegant algorithm, as you'll see later on, that is actually able to perform tasks that we weren't able to solve before using a probabilistic framework. So today we'll look at first the Gaussian distribution. Actually, before we motivate the Gaussian, um, uh, let's actually start from the beginning. Hmm, what's today, the 18th? So for the SLAM problem, what are we actually trying to solve? What is the actual goal that we're trying to achieve?
We want on our cleaning robots more efficient, not cleaning the overlay area in the house.
Uh, Not really. It's more general than that, first of all. It's not just related to cleaning robots. Also, even if we're talking about cleaning robots, what did you say? What you wanted to avoid for the cleaning robot? What was the problem?
Yeah, the cleaning robot, if you have a built-in cleaning robot, it will clean the very limited area in your house and not going to clean the area you didn't clean.
Okay, in order to be able to cover the entire house or room, He would need to have SLAM, that's correct, yes. Mhm. But it's more general than that. I would argue that being able to move through the environment, being able to navigate through the environment, is one of the fundamental features of any mobile robot. So the SLAM problem is the same whether you're talking, or it's similar, whether you're talking about a autonomous car or a cleaning robot or a humanoid robot walking in a factory. All of those require often a solution to the SLAM problem or an approach to the SLAM problem. So we're talking about simultaneous, localization, and mapping, right? So what do these terms actually mean? What is localization?
To locate the position you are where you need.
Correct. Your current location, in a sense, right? Within an environment. And mapping. What is mapping?
Create an app.
Yeah.
As big as you can do the platform.
Yeah. Mm-hmm. Now, there's a couple of things when we talk about these terms. Let's just discuss those first. So first of all, let's talk about if we want to define what we mean by navigation or being able to navigate. I would argue it is the robot must be able to move to the right position at the right time, and that's sort of a fundamental skill that it must have, because otherwise, how would it be useful? Even if your robot is at the right position, but 2 days later, it's not so useful. So to be able to do that, it relies on being able to localize and map the environment around it. Now, this is sort of like a chicken and egg problem. Because if I have a map of the environment, then I can find my position or pose, uh, usually easily enough. And if I know my position, then I can map the environment around me. Actually, so let's make a simple environment with some landmarks of yellow, green, and blue. Okay, and how do I draw a roll? Oh, here's my robot, and how can I draw a straight line? Vectors, I guess what? So here, if I have a robot and I have a sensor that can detect the landmarks, and for those landmarks, I get position and distance. So then that looks like that, right? If I know the position of the obstacles, let's draw those in. So let's say this one is at 0.5 and 1, 2, 3, 4, 5. And this one would be at 1, 2, 3, 5.5. Yeah, cannot go smaller than 12 for some reason. Then this would be 0, here we have this will be 0, 1, 2, 3, 4, 5, 6, 6.5, and 1.5. And this will be 6.4, 3.5, and 0.5. Never mind, I'll next version. Okay. Then with just, if I use triangulation and I know the distance and the angle to the various landmarks, then I can localize my robot and I can get the pulse of the robot. Similarly, if I don't have that information, then I can do it for let's say this is 1, 2, 3 meters and minus 30 degrees. Oh, 5 meters and 20 degrees. And on the other hand, if I know my position, and in this case, we would need to know the 2.5D position, so also our orientation, say we call that 45 degrees. And the angles, then I can figure out what the map of the environment is. Okay. So those are the two possible versions of this particular problem. And we need to somehow break that issue that we need to have a map in order to do our localization, and then if we have the localization, we can do a map. So we need to combine both problems and solutions simultaneously. So what we really want to do is to have the ability to construct this. What did what numbers did I use this? 3.5? And then this one was 4.5 and 0.5. Yeah. And so now, so now I have an estimate of my poles. I have some of the landmarks, and then my new landmark here, I can localize. I can put in the map by sort of solving my localization problem with the map that I currently have, and then adding accumulating additional information as I navigate through the environment. So So this is what SLAM is all about, right? We want to drive around a little bit and then find our location. Once we have our location, or with the information that we have about our location, we want to start building a map. So why is that difficult? Why do we have a whole course in graduate studies just about the SLAM algorithms?
Because the Denmark won't tell you the exact procedure where you do.
Okay, so we have noise in our sensors, right? Yeah. What else?
Okay, the sensibility of the agent is limited.
The Yeah, so the sensor range is limited. So on here, for example, the little robot cannot detect the blue landmark here, right? It's outside of the range. So there's noise in our sensors. There's the limited range in the sensors. And there's also noise in our actuators. Right? So if I tell the robot to drive forward by 1 meter, then it's going to move forward, guaranteed not by 1 meter. So that noise is a problem. And but the most difficult part of this is the most difficult part of this is
of the landmark are indistinguishable.
Correct. The landmarks are not unique. So I need to figure out which sensor reading goes with which landmark. So this is called the data association problem. So it looks like this. And if you make a mistake in your data association, so if you think you're looking at landmark 1 and 2, but in reality, let me get rid of all of that. No, that's not the one I wanted. In reality, we're down here, then um, the map will be entirely useless. But you can see that from both of those locations, the sensor readings will be the same. So how bad is this data association problem? If you get it wrong, it's very bad. But I mean, computationally, how expensive is it to do that?
Uh, in the aspect of computation, now, yeah, you need to adding additional memory to tracking the history of the uh, landmark position to make the non-distinguishable landmark to be distinguished.
Um, I still, even if you keep a memory, I think I can definitely make it fail. So I don't think adding memory alone is sufficient. I think adding memory can help, but if you have this kind of environment, oh, how do I do that? So I put the robot here, right? And then one step later, your robot is here. Now, whether you went and the command that you gave was to drive straight forward, right? So this is where you expected to go, but you ended up either here or there, then the history alone is not going to help you be able to distinguish those.
Yeah.
So the history can help, but I don't think it will solve all of our problems. So now when our robots operate, if we look at data association from a computational point of view, then basically we have a problem where we're given n landmarks, and to make it simple, n sensor readings. So what is the worst case complexity of finding the optimal mapping?
They all circular around you.
No. I mean, you have n landmarks,
Yeah.
right? And then you have n sensor readings. Now, you need to back calculate from that, but you need to first know which sensor reading goes with which landmark, right?
Yeah.
So if you do that, and then you can calculate how well does the current map match the sensor reading, then you can pick the one with the minimum, right? And then that will be your best estimate for the location. But what's the worst case complexity of finding the optimal best mapping for landmarks to sensor readings? Like, how much work do I have to do?
There's order of convolution.
Order
Of n and
factorial.
yeah, necessary.
Yeah. So how much work do I have to do? Well, that mapping would be, for the first sensor reading, I have n possible landmarks I can map it to, right? For the second sensor reading, I have how many mappings I can map it to?
-1.
Yeah. Because now 1 is already used up, and then n minus 2, all the way up to 1, which is order n factorial. So, okay, if we try and implement this and our robot runs in an environment with about 60 landmarks, then how long would that take? And what kind of computer do you need? Because my robot takes sensor readings from the environment lots, right? Sonar readings, cameras. So 60 sounds like a reasonable guess, right? So how long would that take to compute if you calculate 60 factorial combinations? What do you think? Would you be able to do this in real time on the robot?
Depends on the equipment of your robot.
Not really, no. It doesn't really matter if you use a embedded system like a NVIDIA Jetson or a more powerful i5, i7. It doesn't even matter if you have access to a supercomputer on the cloud, right? It wouldn't even matter if you have access to a billion supercomputers in the cloud. And even if those computers would run a billion times faster, it still wouldn't make any difference. Because n 60 factorial is this. Right? This is an enormously large number. Okay? There's no way that even in a billion years you won't be able to calculate this, right? To do this mapping. Do you know any other problem that has a complexity of n factorial? One famous one, which is in the category of NP hard or NP complete, I'm not sure is the n queens problem. Have you heard of that problem before?
Eight queens problem.
Yeah, and if n is 8, then yes, it will be the 8 queens problem. That's what you have in the chessboard. So the n queens problem is the problem of placing n queens on a n by n board so that no queen attacks any other queen. Okay, I can put in a link to the Chinese version of the Wikipedia page.
There is a English page just below.
Yeah, but that's actually the 8 queens problem. I wanted the n queens problem. Okay, actually it talks about that. So close enough. So why does that have a complexity of n factorial?
Because you put the queen on the chessboard because the selection is decreasing along with you putting the queen check.
Right, but when you your initial attempt would be an algorithm that searches through the board, right, which would have complexity n by n. Right? So you would think that initially you have n by n possibilities, right? However, through clever representation, you can reduce this to an n factorial algorithm, because if I think about the board, and now I want to place queens, then that would be I have n by n choices initially, right? However, after you place a queen, it's clear that the queen will block up this entire row, this entire column, and this entire row, right? No other queen can be in this column or in this row. So that means that one of the queens must be in row 1, right? And one of the queens must be in row 2, and in row 3, and in row 4, in row 5, all the way up to n. Right? There can also be not two queens in the same column, which means that every entry for a column is only a single number. Right? There can never be two. If I specify these are the queens in column 1, column 2, column 3, column 4, it's exactly one queen in column 1, exactly one queen in column 2. So that means that for the increased problem, I don't have to think of it as an n by n board, but I can think of it as all the combinations of a list from 1 to n. And then that representation, if I have a representation 2, 3, 2, 4, 1, then that would mean that in column 0, or in column 1, the queen is here, in index 2. In column 1, it's at 4. Okay, I didn't draw 0, 1. In column 2, it's in 0. So then that will place a queen there. And then the next one is here. Right? So that's a pretty clever representation to greatly reduce the amount of work that we have to do. It's still an enormous amount of work. N factorial is not a good complexity, but it's a lot better than n to the n to the power n to the n. So through clever representation as a column vector, to be order n factorial. So it's the same as the data association problem. Okay, now people have looked at this problem. For 8 queens, you can usually work that out. You can find a solution. Also for higher ends, but to count all solutions, People have been working for many years on this problem. What do you think is the largest board that we know all the possible solutions for? Which basically means that we have to solve, we have to go through the entire n factorial computation. I have to enumerate all the possibilities in order to check them, or almost all the possibilities in order to check them. Actually, they use a clever algorithm that uses symmetry of the board and rotations of the board to speed it up. So they didn't actually have to go through all of the n factorial combinations. They only had to go through most of them. So what's the largest n we know the solution for? What do you guess? 10, 20, 30, 40? So 8 is trivial. We can calculate, we can run through 8 fast enough. Even if I just write the program in Python here and use itertools.permutations to check, that will run quickly enough. As far as I know, and it's on the board, I think, it should be in the Wikipedia article. So here are all the solutions for the 8x8 board. They consider fundamental solutions. So for n by 8, it's manageable, up to 20, okay. And the largest we have is 27. So this means, and if you look at the 27 solution, right, this was about 50 FPGAs, special purpose built hardware, to work on this problem that ran for a year. Right? So there's absolutely no hope. So from N27 to N28, right? How many years would that run then? If they want to, now they have the system, right? They can just try and solve it for N28. How long would that run, do you think?
28 times.
Yeah, about 28 years. Right? So I think they're not that patient to wait for this. So up to 60 would be 60 times 59 all the way down to 28. Right? Completely hopeless, like astronomically large number. So there's no way that we can solve this data association problem in a brute force manner, which is really the problem with SLAM. That's why we need to use other kind of approaches. So the largest known solution by the Q27 project and they didn't just use fast hardware, they also used very clever algorithms to do that, highly specialized hardware. So if you're ever considering an algorithm to solve using factorial complexity, then if n is larger than 20, it will be extremely difficult on commodity hardware. But 10 you can solve easily. So just to put in a number, for how long that will calculate. So the N, the Q27 team, were able to solve N factorial is equal to 27. So right? So they solve this size. And you can see how much smaller this is compared to 60 factorial. But just out of fun, for fun, it took them 1 year, right? So 1 year is units per second. 1 year is 365.25 days, right? Each day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. So that would be the nodes per second. For that computation, and we assume that checking whether the queen's fit is the same as the data association problem. Actually, I have, of course, I think it's much harder to do the data, to check the geometry, like computationally, there's more computation to do than for this problem. But maybe you could, so that means they actually expanded the nodes per second. They expanded 3.45 times 10 to the 20. So that's extremely fast. If you do any kind of AI search algorithm, SLAM problem, then usually you talk in the order of maybe 1,000 to 10,000 nodes per second that you sort of grind through with standard hardware. This is many nodes per second, but much faster than I actually would have expected. So,
Professor Carolina said you cannot access the channel. And I find your recording hasn't started yet.
oh, but we're recording there. I thought we were recording there, right?
Oh, yeah.
She cannot access the channel.
Yeah. You said you, I think
How come there's so many people there?
it fell.
Okay, no, okay, now she should be able to.
in the hospital.
In the hospital, okay. Hope she's doing better soon. So the time that we need to calculate would be what? Actually, so second per node. So this would be math dot factorial 60 multiplied by second per node. And just because we're generous today, I'll give you a computer that is a billion times faster than they have, right? So that would be the time divided by 10 to the 9, right? So this is how long we would calculate. Um, so that's in seconds. So it's this many hours. Okay. This many days. This many years. Okay. Now we're at years. So now this many thousands of years. Um, okay. Not thousands of years. Millions of years. Billions of years. So how old is the universe? What's the estimate for the age of the universe? Or how old is the Earth? Yeah, about 5 billion, 4 billion years, 5 billion years, right? The universe about 13 billion years. So this would be the lifetimes of the universe, and it's 5 to the 10 to the 30. Um, so there's just nothing in human experience that would be that big that you could enumerate. Another number to keep in mind, if you deal with complexities like that, or if you're considering them, um, what is 10 to the power 80? Oh, where did we have 8 point? That was here. Had that come out? Okay, sale on the. Okay, this is even better. So many billions and billions of times the age of the universe is how much you had to calculate. This number is good too. 10 to the 80, because 10 to the 80 is equal to the estimated number of primitive subatomic particles. So atoms are made up out of quarks, yes, and there's other ones too that I don't even know, muons and a bunch of other ones, right? So atoms are made up. Actually, atoms are made out of electrons, neutrons, and protons, and those are made up out of quarks. And 10 to the 80 is the estimated number of quarks in the entire universe. So if you wanted to solve mass factorial 60, you would have to go and label each one in the entire universe. Not just once, but you would have to do it 80 times. And then you'd be done. So, yes, truly an astronomical number. So don't get, even though 20 factorial doesn't look so bad, right? That doesn't look like such a big number for a computer that can run at gigahertz. But it will run for, it'll sort of be the maximum computation you can do on a laptop if you run it for several months. And then 21, okay, that's 21 times worse than that. So if you computed this for a year, then it'll take 21 years for the next number up. And of course, 22 would take then 400 years off. And also 10 to the exponentiation is really that hides a lot of the complexity, because 10 to the 80 doesn't sound so bad either. Until you realize, sort of, if you try to relate it to things in the world, what a truly astonishingly large number that is. Now, what will be our simplest approach to localization, though? Well, the simplest approach would be to remember the movements that you've made. So that means remember your motion commands. And then integrate the motion commands to get the current pulse. Now that would work if there's no error in the actuators, in the motion commands. This is called dead reckoning. And sort of what people had to do before we could shoot the stars and navigate to navigate across the ocean. We wouldn't really know, or if you had to navigate across the ocean without GPS in the old days under cloud cover. That's why that worked on those distances, but they also had huge error by the time they came up on the other side of the ocean. So this would be an open loop approach where we don't actually need any sensor data. And humans can do that kind of navigation as well. I just don't think we are very good at it. Like you can try that yourself. If you just stand up, come here. Okay, stand there. Face this way. Okay, and close your eyes. And then turn 45 degrees to the left. Okay, that's more like 90 degrees. Close your eyes, it's okay. Okay, turn 45 degrees to the right. Okay, then go forward by, okay, let's call that 50 centimeters, 2 squares. And I'll make sure you. Whoa! Okay, should have been here. Okay, turn 180 degrees. Move away. Okay, then go forward half as far as you went before. Okay. Yeah, pretty good. I think that was luck. Usually, if you close your eyes, it's quite difficult to navigate. What do we use in order to do this navigation? You can sit down. Okay. How can he navigate? How can he do that reckoning with his eyes closed? So presumably there's no feedback, right? Like you could say that with my eyes open, I can check how far I move, right? Because I can see the chairs moving, and I can see the wall moves and the overhead, and I can see the people moving in my vision, right? But if I close my eyes, then what feedback do I have about the environment around me?
The sound of progression.
If I keep talking, yeah, that's true. We can localize sound. Uh, I would say coarsely. I'm not sure how good we humans are at localizing sound. I certainly, okay, come here. We can do a test. Okay, now you just talk. Try and talk with the same, or actually, you stay, close your eyes, and I'll talk, and I try and talk with the same volume, right? So that I don't raise my voice, I don't talk softly. So I try and talk with the same level, right? Yep. So we call this 1 meter now, right? Yep. And then tell me if I'm getting closer or further away, and or if I stay the same.
Yeah, you're
Hello? 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 Can you hear me?
yeah, I just need to remember what you did me more apart. The word.
Oh, the word, yes.
Yeah,
I walked away from you.
Yeah, walked away from
Yeah. And by how far?
How far?
And where am I now?
Yeah, you are close.
Okay. And how far away am I? Can you still hear me now?
Yeah.
Can you still see me now?
Yeah, you're far away from me.
Far away, yes. Yeah. Good.
Yeah,
So,
yeah, I think it's because the echo of the the classroom will help.
the echo, yeah, maybe. Yeah. Yeah.
Hard to test.
Okay, but if it's quiet and I close my eyes, then what do I use to navigate? The feet, yes, my proprioception. I sort of know, right? If I take a step forward and I walk, then I sort of have an idea of how much that moves, right? Anything else? If you come here then, and we do another test, you, yeah. Then just sit down and close your eyes. Okay, so now he cannot measure his motion with the feet, right? Then you tell me if you detect that you're moving something. Okay? Okay? Yeah. Backward. Turn around and go back. Yes. Okay, so how can you do that? Okay, thank you.
By
Cerebellum. It's actually your equilibrium sense is in your ear, right? So proprioception in your ear, you have little hairs and basically a hair water bubble, and as it moves, that tells you also about your motion. However, that sense is very easily fooled. So if you want to do, if you want to try that out, then you can go to, but do it on grass, don't do it on concrete. And you may not know that game where you give somebody a cup, you hold a cup, and then you ask them to run around and look at the cup, right? Then you ask them to do this for 45 seconds and then tell them to walk straight or run straight. And then what happens?
Okay, very steady.
Yeah, you can definitely not run. Most people will fall. And not only will you fall, but if you want to run this way and you already know something is wrong, right? You know something is wrong. So you think, oh, I'm going to have to head towards the right so I don't walk to the left. You still end up running like this, right? And then you take 3 steps and then you fall down. That's why you want to do that on the grass. And we did that test with the NTNU junior team, but so they are like, we teach them educational robotics to, how old are they? 8, 9, don't know, I don't check. 12, really? Young kids. But they cheated me, right? Because they just run around like this, and then of course you don't get confused. And then I tell them, no, no, you have to look like this. Go, 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 go. And then I go, go, go. And then I'm the one run off and just boom. And luckily, I did it on the grass there, and I didn't run into the tree. Otherwise, I would have hit the tree. So it is. This is just for fun, and usually if you have, if you are careful, then nothing bad will happen. Like you fall down, but nothing major would happen. However, if you become a pilot, and there's different licenses you get as a pilot to fly different kinds of planes, depending on how much training you have, and also what equipment you have on the plane. So the big passenger airplanes, of course, they have inertial navigation systems, GPS, redundant systems, and everything. So they have no problem flying through clouds. But if you fly one of the small airplanes, then your instructors and the examiner, they will tell you that if you are not equipped for flying through clouds, and you fly into clouds, then you have about 60 seconds left to live before you lose control of your plane. It is extremely quickly, and they do tests, like during training, they fly, and then the other pilot takes over, and then they ask you, with your eyes are closed, and they just fly, and then they ask you, okay, where's up, where's down? And you have no idea. So before they develop the correct equipment, the correct sensors to be able to fly planes safely in clouds, yeah, unfortunately a lot of pilots died getting caught in clouds, flying from clear sky into clouds. Because then in the clouds, it's not like it's just like clear sky, only you cannot see. But because of the winds, there's lots of shaking going on and lots of acceleration in different directions. So you get confused very, very quickly. And nothing you can do, no reference that you have. So human proprioception is very easily fooled. Not something you want to rely on. navigation. Now, some other animals have some amazing navigation capabilities that are even better than those of humans. And I give you the sound, so that was. And there's some crazy stories about pilots. Like there's with the advent of radar, they were able to track the planes then using radar. And there's one story where the pilot flew into clouds that got confused. So he didn't know how to control the plane. And he called up the tower, and the tower could see him on the radar. And he says, "Yeah, I know exactly where you are, but I cannot help you because I also don't know if you're upside down or not." And this guy said, "Oh, please help me, please help me." And then crashed and died. And actually, it's not just vertical. early aviation. What about other animals?
In long distance navigation.
Yeah.
I think they all make use of the sunrise and sunset to navigate the direction they are moving.
I think they can do it also in clouds. But yes, they would use sunrise, sunset, yes. More naturally or more intuitively than humans. Magnetoception. So the homing pigeons that you have in Taiwan, I guess they're pretty, or at least I see lots of places with homing pigeons. You know homing pigeons?
Like a pigeon, but very fat pigeon.
No,
Or you
I don't think it has to be a big pigeon.
you mean the bird that light and were nested on everybody who under the human.
They have little houses for them and they have competition, so they take the birds out to sea, release them on the boat, and then the pigeon flies back home. That's why it's called a homing pigeon. Or before you have before you had SSH and encryption and secret codes, the spy would have a homing pigeon, and then they write the note, put it on the. Even during World War II, that still happened, right? So one pigeon from the UK got like an award because it delivered an important message, and afterwards they found out that it was attacked by a dog, and it was attacked by a hawk or an eagle, but it still managed to get the message to the headquarters. So that's a homing pigeon, and I think I don't think we have any. Or when I grew up in Germany, I never knew we had one, but here in Taiwan, I think they're more popular. And I heard that they used to have competition where the bird has to fly from Kaohsiung to Taipei. And then there's like one place, and they can do that using magnetoreception. Pigeons can actually measure the magnetic field.
But what's the difference between the homing pigeon and the regular pigeon? They all look the same.
Then it's the same bird.
It's the same bird.
It's just one is trained to fly back home.
Oh.
If I go to another pigeon and throw it out, it flies, it doesn't have a home. It's not trained to fly home.
About a lot of teachers reject almost fly out to the sea. Almost literally stuck in the sea. And then
Right.
if a region can come back, they're almost extinct.
Right. Yes. Yeah, I mean 500 kilometers is no joke.
But it's
That's
not friendly for the
No, and also I heard the reason why I have to go to the boat now, they cannot do it from Kaohsiung to Taipei anymore. They have to go and use a boat because people, if you have a good homing pigeon, they can make you a lot of money. So people catch the homing pigeons. So then some guy in Taichung, like from Kaohsiung, then the bird is a little bit tired, he throw up a net and catch the bird, and then I don't know what they do, ransom it or something. Only in Taiwan, I guess. But anyway, the bird can do that because they can measure the magnetic field. There have been some claims that humans can do that too, but none of them have so far, as far as I know, stood up to peer review. That's more like in the area of people can read other people's mind. Um, if there is any reception for the magnetic field of Earth, it's certainly very low because there's no sensor that, if I close my eyes, where is north? I have no idea where north is. I wonder what whales use. They also have enormous journeys, right? Thousands of kilometers through the oceans. Um, they also must have a very well developed sense of dead reckoning because in the ocean there is also no landmarks. They do use sonar, like active sonar, I think. They actually produce sounds and then wait for the back.
They can up to the water surface. They can see the sun.
I don't think they see much. They're very deep. At that depth, I don't think you can see the sun anymore. It's completely dark.
So the
past 50
whale
meters.
can breathe out.
Yeah, they come up to breathe once every couple of hours.
Yeah, so they can check.
They can check. They could check, but I'm doubtful that that's what they use. Um, so bats and let me check what whales use. Hunting, navigating. So they seem to use sound for navigation as well. And bats, whales, dolphins. Can use echolocation. So some humans also were able to learn echolocation, some form of echolocation. Okay, so if we compare that to the robots, then what sensors do we use in the robots? So what sensors do we use on the robots?
LiDAR.
LiDAR, yeah. So what is LiDAR? What do we actually measure with the LiDAR sensor?
We scan from our sound with point or only what on every one every object.
Every object. I don't think LiDAR can actually do object recognition or anything like that. So we get the feedback about individual points, but you won't get like chair at this location or anything like that. You would have to do a lot of processing before you actually have a perception like chair. The raw sensor data from the LiDAR is actually of time of flight measurement of a laser beam that is sent, is emitted by the sensor, LiDAR sensor. So we send out a laser beam and then we wait until how long it takes to return. Now we get the position and basically when the thing lights up then it hits something. Um, so there's that sensor. What else?
Camera.
Camera, yes. For visual feedback, yeah. What else?
Gyroscope.
Yeah. And if
if you say gyroscope, you might as well just also include accelerometers, right? Because they're very similar. IMU, inertial measurement units. So what do they measure? What information do we get from a gyroscope? Yeah, partially correct. What velocity? Angular velocity, yes. Accelerometer gives us no. Otherwise, we would call them velocity meters. So for accelerometers, we get
acceleration.
Yeah, linear acceleration and IMUs. What is an IMU?
Orientation.
Hmm?
Orientation.
Yes, but IMU is basically a 3-axis gyroscope, 3-axis accelerometer with an embedded processor that integrates the readings for you. Because in order to get your current angle, right, if you get, okay, break it down into 2. If you get the velocity reading, in order to get your angle, then you have to you have to use the integrate the sensor readings in order to get your current angle as well as linear velocity. In particular, the linear, they sort of work in tandem because your gyroscope measures angular velocity, and it does that a good job if your angular velocity is high. Then it can measure it very accurately. If your must integrate the reading to get angle. So the problem is if angular velocity is, what's the problem with the gyroscope then? Not the gyroscope will drift, but your angle. After some time, right? Because you add in all these measurements from your gyroscope, but mostly if you're stationary, then your readings are going to deviate a little bit. So when you go 0 degrees, 90 degrees, 0 degrees, 90 degrees, 0 degrees, 90 degrees, if you do this repeatedly, after 30 times, then you tell your robot to go to 0 degrees, it's going to sit like this, right? Or like this. Because the integration, the noise will sort of accumulate. So that's a problem with the gyroscopes. And accelerometers. Now accelerometers measure linear acceleration. So that doesn't sound so useful in itself, right? Because in order to get the position, you would have to integrate it twice. Because if you take the acceleration, you integrate it, you get the linear velocity, and if you integrate that, you will get your position, which would be very noisy. However, the accelerometer, one of the key features, or one of the good ideas, one of the, what do I call it, most important feature, capability, is that it can measure, what do we usually measure with our accelerometers?
Force.
The force, yes. And which force would be applicable to the robot? For us, usually it's gravity, right? So that means by looking at the force that is acting, I can if there's no large linear motion, I can use the accelerometer as a tilt sensor. And I can use that to reset the gyroscope. Because with the tilt sensor, if I can measure gravity and I know this is 0 degrees, I can then reset my angular velocity integrator and say, now you think you're at 10 degrees, but really you're at 0 degrees now. That only works, however, if we don't have other acceleration. So if somebody keeps pushing the robot, applying some external force, then that's a lot harder. Also, what data do we get from our LiDAR?
LiDAR. LiDAR can measure the distance between the sensor and the object you understand.
Yeah.
They can.
So we get a point cloud, which tells us the closest thing to the robot along that particular line. So if I have a LiDAR sensor and I can sort of get a scan in one plane, then I can tilt the sensor to get multiple planes, right? I can measure what's the closest thing from me to the robot along every particular angle. So if I run a scan here, then on this part I would get very close reflections from the chairs and the table, and then this would go out to the wall, and there I would get some medium distance reflection. Now, that can be measured with very high accuracy, which means it's the most powerful sensor that we sort of have for navigation. And SLAM nowadays, the SLAM problem, if you have a LiDAR sensor, then it's basically solved. Like there's good ROS packages for doing Hector SLAM. There are good ROS packages for doing the SLAM if you do have access to a LiDAR sensor. If you want to do it like us, with just using vision, then that's a lot harder. Still solvable in 2.5D. Talk a little bit more about the complexity of it later. Okay, what other sensors do we have on our robot?
Real sensor.
Wheel sensor, yeah. So that would be like proprioception, sort of. Right? If we have wheels or sensors for the position of our joints, those can be high accuracy. On a good surface. But if your surface is bad, then you have wheel slip, then you get more noise. When we started the robot competitions with our toy cars, I think I showed you the video before. So this year, some of our early work when we started competing at the RoboCup soccer competitions and things like that, we used the camera, we used the toy car. Now the toy car, if you tell it to go forward, we didn't actually have any shaft encoders. We had to use the vision system. Our competition was using specialized rubber mixtures in order to reduce the amount of wheel slip that they had, and they used high quality shaft encoders. So not even those. It was before that. So 15. Robotics. Anyway, you can have a look at this.
Writing is not that easy, but rarely can help. Quick sentence is grammatically correct.
Yeah, no. Anyway, we were playing on a hardwood surface, and they had special diagnosters, so they could actually use dead reckoning for about 5 minutes before their robot was really, because before the error was so high that they would start missing the ball and not scoring goals anymore, right? Because they had very high accuracy shaft encoders and they made sure that there was no wheel slip. Then in 2003, we moved from hardwood surface to a carpet. And lots of other teams had similar systems, right? So those teams were all complaining like crazy, like, oh, impossible, like we have to use the vision system, has to be so much better because the wheel slip, like we can only drive for 30 seconds without getting lost, right? For my team, it didn't matter at all because we had no shaft encoders. So we were all very happy about moving to the carpet surface. So if you put in enough engineering, you can get the shaft encoders and dead reckoning actually to go really well. Because at that time, they can drive the robots then very fast, faster than we can track them in the vision system. So they only used the vision system to find the ball, whereas we were actually looking for all our robots, figuring out the idea of the robots and everything. Something that they didn't have to do until either they had to drive on carpet or even worse surface. But there was a lot of discussion, a lot of arguments. They really were against this. But I think, of course, as far as AI is concerned, then you want to be able to play on any surface, not just on this one special wooden surface that you tuned your tires for. And now they're all playing on carpet, and they use the Omni wheels because now the vision systems are better, so they don't need to use the high quality, accurate localization anymore. So, but on a good surface, yes, you can go a long way with just having good shaft encoders. The shaft encoders could be global or relative. Okay, then other sensors. Also used to use ultrasound sensors. They're still useful for but nowadays, most of what we used to use ultrasound for, we can use cameras now, and we have good enough algorithms and fast enough processing to sort of get the same information. But more recently, and I guess that's sort of the most modern kind of sensor, are RGBD cameras that combine time of flight or structured lighting to get pixel color and distance. Those are also very powerful, so there's like the Intel RealSense. But that one, I guess economically it wasn't such a powerful product. Because just 2 weeks ago they announced that they're shutting it down. So now it's discontinued. So these are the sensors that we use on our robot. So those are the ones we can use in order to run our localization and mapping. I wouldn't call it a solved problem. It's not a trivial problem, but LiDAR-based SLAM in 2.5D is very common nowadays. Like my robot, my cleaning robot, uses a LiDAR to map the apartment, and it is very accurate and really never fails. It's an amazing robot product for $300 when you think about it. Like none of my robots will be able to run day after day and not get lost. Sometimes it gets stuck in the bathroom, but that's because there's a ramp that it has to go over, and if the battery's too weak, it won't be able to come back. But the LiDAR part, the SLAM part, works beautifully. Like never any error in that. So it can map the environment, the apartment very well. Visual SLAM also, there are efficient ROS packages or LiDAR-based SLAM. software SLAM is probably the most famous one. Or the most well-maintained one.
Your robot has open source algorithm.
My robot?
Yeah. The, you just mentioned the cleaning robot using the light algorithm.
I have no idea what algorithm it runs. It's from some Chinese company, so I'm more worried that they sent the information about my apartment to China. So, and it's the robot definitely is not open source, so there's no way that. I mean, if I were motivated enough, we could reverse engineer the firmware and then find out what algorithm they're running. I assume they're running this standard particle filter mapping algorithm. I don't think they do anything special. Like I said, the whole robot is like 300 US dollars.
All the cleaning robots.
Yeah. Yeah.
None of it can be open source application.
They may have used open source software. So the robot doesn't run ROS as far as I know. I think they developed their own system just to reduce cost because something with the sensor that runs at reasonable speed using ROS would be a lot more expensive than some custom solution with a small ARM 4 and 3 or 5 or something. Like most visual algorithms, or like all visual algorithms, the more control you have over your environment, the more you can control the lighting and the kind of objects that are in the environment, the better it will work. But 2.5D it's harder, also doable. 60 SLAM for drones. So if you have a drone and it's flying around, that is then a 6D problem, right? Because you have X, Y, Z, as well as tilt, pan, and yaw angles that you need to estimate for your pose. And usually the power consumption of a LiDAR sensor is very high, so very few teams or very few robots can actually mount a LiDAR sensor on the drone. So then they use RGBD or auto landing is using ultrasound usually for specifically for landing. So I think that's more like the state-of-the-art research. So there's still more active research in 6D SLAM now than there is on 2.5D. I don't think there's many new papers and breakthroughs coming out of LiDAR-based SLAM in 2.5D. It's sort of a fairly, very well understood problem now. 6D SLAM is still more actively. Explore and research and they would certainly like to use vision in order to do the localization on the drones. By the way, one thing that I completely forgot about here is what other sensor do we have for our robots? In cars, we can use GPS outdoors. So that is actually a very powerful sensor. Um, and used extensively in autonomous driving, of course. Or even more so in autonomous modes. So GPS works how?
By calculating the satellite delay of the signal.
Yes, so it basically calculates time of flight from satellites in orbit. So that's why it only works outdoors. Indoors, it's so then that would be called an LPS. That is of more interest at the moment. So lots of large factories and plants and warehouses, they want to use robots in order to run the warehouse. For that, they need a local positioning system because it's indoors, and that's still also an active area of research. Um, they usually use vision-based systems with human-designed landmarks. So then that problem can be significantly simplified by having the right markers, like Aruko markers or something like that, that your vision system can detect easily, and you can detect the pose to the marker easily. That's much easier than random office environment or a random environment outdoors, like going through a forest or something like that. Okay, good. So we didn't manage, we end up not being able to cover the Gaussian distribution, but we'll do that next class. So that's it then for today. Signature. Oh, okay. Monday 26th. The relative angle to the robot is just if the head of the robot 0 degrees, and from the robot point of view. Like here, if this is your environment, right? And your robot is theta at 45 degrees, right? It's a robotic. Yeah, the robot is facing 45 degrees down. The camera is looking this way. Then this may be off by 30 degrees. Then this would be your relative orientation, your relative angle to the and these are for 45. Correct, yes. And if the robot is facing this way, then it would be 75. Yeah, mine is from the point of view of the robot,